Hello my good viewers and welcome back to our YouTube channel. Of course, this is the #1 online channel that gives you the best tutorial. In our previous discussion, we introduced functions where we actually gave the definition of a real valued function. We went ahead and presented functions graphically and in form of tables and formulas. We also try to inspect some graphical representations to see if they actually represent functions. We did the same to tables and formulas. We finished by introducing the piecewise functions, where we actually defined a piecewise function, do a graphical analysis of the piecewise function. So here we are today talking about the domain and range of a function. And basically, like we said last time, that the domain of a function is basically all the set of all possible inputs where the function is defined. But in this tutorial, we are going to dig deep with the domain and range of a function. So you realize, suppose we have a function, we have what we call the implied domain and the explicitly defined domain. So an implied domain is the set of all real numbers to which the equation is defined, and whereas the explicitly defined domain is one that is given along with a function. So we can write and say the implied domain is the set of all real numbers for which the equation is defined, whereas an explicitly defined domain is one that is given along with the function. So that is basically the difference in implied domain and explicitly defined domain. So an implied domain is the set of all real numbers to which the equation is defined, whereas the explicitly defined domain is one that is given along with the function. Maybe we can have an example. And see what do we mean when we say the implied domain and the explicitly defined domain. Suppose I have a function g of x, and this function g of x is a rational function where it is defined by 1 over x squared minus 4. And we are saying such that 4 is less than or equals to x and less than or equals to 5. So you realize the x is defined in terms of range, that x actually ranges from 4 to 5. Here, we mean that x lies between 4 and 5, and thus this function has an explicitly defined domain. So we say the function g of x has an explicitly defined domain. The inputs, and the input here is x, is defined by the given range, that is 4 to 5. That is, x lies between 4 and 5. So therefore we say our function has an explicitly defined domain. Suppose we have the same function, g of x is equals to 1 over x squared minus 4. And we realize this function is defined at some points and it is not defined at some point. What is that point that this function is not defined? When I say the function is not defined, I'm trying to say that what is that input that will not give us an output? What is that value of x? When you substitute to this function, you will not get an output. And you realize if I substitute, if I work out on the denominator and I get a 0 on this denominator, it means that I'll be having 1 divided by 0. And we know that the division of a number by 0 is impossible. So that means that there is a number, that number that when I plug in here to replace x, to represent x, will give this whole denominator to be 0, is the point or the input where the function is not defined. So I'm saying when I have x squared minus 4 is equals to 0, then this function will not be defined, such that x minus 4 should not be equal to 0. And this means that x squared should not be equals to 4. And this means that x squared should not be equal to plus or minus 2, because we said the square root of a number can be positive or negative. So this means that x squared cannot be 2 and x squared cannot be negative 2. So you realize that these two here are actually excluded from the inputs values, and that is how we get the domain, such that the domain of this function now will be all set of real numbers except 2 and negative 2. So I can say, and because we have actually determined the domain of this function, that the domain was not given along with the function, this domain is what is called the implied domain of this particular function. So we can say the function has an implied domain, and it is given by the domain. This is how we denote the domain, like we introduced last time. The domain of the function g is the set of all real numbers, x is in real numbers, that are such that x is not equals to plus or minus 2. This is the set of all possible inputs that will give us an output. And this domain excludes positive 2 and negative 2. And that is why we are saying the domain of a function is, the natural domain of a function actually is that domain which will give us input that will give us an output. So basically, this is how we find the domain of a function, but we will have many cases where we'll be looking at various functions and see how we can get the domain. So this is all about implied domain and the implicit domain. The implied domain is one that is not given along with the function, but actually is the set of all real numbers for which the equation is defined. Whereas the explicitly defined domain is one that is given along with the function. So let's generally discuss about the domain and range in layman's term and get to understand it better. So basically we can say the domain is all inputs values. So we can say in layman's term that the domain is all input values. The set of all input values is what is called the domain. And the range is the set of all output values. So all output values. Basically, that is how we can define domain and range in layman's term. The domain is all input values and the range is all output values. For example, suppose we know that the area of maybe a rectangle let's represent it with s squared. This area of a rectangle will always such that the area is greater than or equals to 0. There is no way we will have a negative area. So the range of this area is actually greater than 0, and the same for the domain. We cannot have a negative input, that is length, a negative length or a negative width. Suppose I have a function y is equals to 1 over x. You realize this function will be defined for all real numbers x except when x is equals to 0. So the domain will be such that x is in real numbers, all real numbers, such that this x is not equals to 0. So this is the domain of this function. Suppose I have another function, let's say f of x is equals to root x. We know that for natural numbers, the square root of a number will always be getting the square root of a positive number. So this means that the function will be defined for all positive numbers except for negative numbers. So this basically means that x will always be greater than 0. So the domain is such that x is in real numbers such that this x is actually greater than or equals to 0. That is how we basically determine the domain. But let's go ahead and discuss more functions and see how we can actually obtain the domain of maybe a rational function and a radical function. But before that, let's have a discussion on what we call the natural domain, which we were basically talking about. Now you realize a natural domain is basically all the input values that work in the formula. All the input values where the function is defined. In simple terms, the natural domain is the set of all possible inputs that will give an output. So you can use any of that definition that all input values that work in the formula. Or we can as well say all input values where the function is defined. Where the function is defined. That is the natural domain. So let's have examples starting from the simpler and going forward. So suppose I have a function f of x is equals to x cubed. I have a function f of x is equals to x cubed. What is the natural domain of this function? What is the natural domain of this function? Basically, it is as if I'm asking what is the value of x that will not give us an output such that we exclude that value from the set of all natural numbers. So you realize all real numbers here will actually give us an output. If we have a negative number, we'll get an output. If we have a positive number, we'll have an output. So the domain of this function is actually, this is how we can write the domain. The domain is such that it is the set of all real numbers. It is the set of all real numbers. You can as well say, you can as well write this, the domain is such that x is in the real numbers, meaning x is a member of real numbers and we are not excluding any. But if the set of real numbers is in between negative infinity, which is also not included to positive infinity. So we can again write this as the domain of the function f is actually the set of x, and this x is in natural numbers, such that negative infinity is less than x less than infinity. This is where now we define the set of all natural numbers. You realize it is less than infinity, meaning negative infinity, meaning that negative infinity is not included and positive infinity is not included, but anything in between them is included in the input of that particular function. Let's have another function, a rational function. For this case, g of x is equals to 1 over x minus 1 x minus 3. G of x is equals to 1 over x minus 1 x minus 3. What is the natural domain, or what is the domain of this function? Like we are saying, and this is important to note for rational function. For rational functions, the function will always be defined except when the denominator is equals to 0. The function is not defined when the denominator is 0. So this means that this implies that in order for our function to be defined, then x minus 1 x minus 3 should not be equals to 0. X minus 1 multiplied by x minus 3 should not be equal to 0 in order for our function to be defined. This is as good as saying x minus 1 is not equals to 0 and x minus 3 is not equals to 0, because the two are connected by multiplication. The two are actually connected by multiplication. Again, this is as good as saying x is not equals to 1 and x is not equals to 3. When I take 3 and 1 to the other side, that is, I'm finding the value of x. So this means that the domain of this function is actually the set of all real numbers except when x is 1 and when x is 3, so not equals to 3. These two values are to be excluded from the domain of that particular function. So I'll come and say the domain of this function is such that x is all real numbers, except for x is not equals to 1 and x is not equals to 3. Take note the statement here. I'm not saying except for x is equal to 1, but I'm saying except for x is not equals to 1 and x is not equals to 3. Immediately, the moment you say except for x is equal to 1, it is as if you are saying that x is equals to 1 should be included in the domain. Very important to take note about that. And in order to avoid the wordy thing here, we can actually write this by saying the domain of the function g is actually the set of x values, such that this x is in real numbers and that x is not equals to 1 and x is not equals to 3. That is also a proper definition of the domain of this particular function. So very important, when it comes to a rational function, the rational function is defined except when the denominator is equated to 0. So that means in order for our function to be actually defined, then the denominator should not be equal to 0. And we go on and determine those points that are giving us zeros on the denominator, such that we can exclude them from the domain. Let's have another example here, and we call this example 3 of now a radical function. F of x is equals to the square root of x minus 1. What is the domain of this function? Now you realize in real number system, you realize we can actually determine the square root of only positive numbers. So this means that our function is defined when we work out x minus 1 it is giving us a positive number. But the moment we get a negative number, it means that our function is not defined. So what does this mean? It means that whatever we are working out with here should give us a number that is positive, meaning what we are working out here actually should be greater than or equals to 0. So in order for a function to be defined, x minus 1 should be greater than or equals to 0. This implies that x should actually be greater than or equal to 1, because when I take 1 to the other side, I'll be having x on this side. So x should be actually greater than or equals to 1. And that is the domain of the function. The domain of the function is the set of all real numbers such that x is greater than or equals to 1. So we can simply say the domain of the function g is the set of x values such that x is in the real numbers and that x is greater than or equals to 1, is greater than or equals to 1. Or we can simply say the domain of the function x is such that x is in the set or in the space 1. You realize this one is included. That is why I'm having the square bracket. It is included because when we substitute 1 here, we are getting 0, and the square root of 0 is 0 to positive infinity. But positive infinity is not included. That is why I'll be having the curly bracket to show that it is not included. So instead of writing this here, we can replace it with this, or we can even say such that instead of having this, we can write in this range such that 1 is less than or equals to x and x is less than infinity. All these mean the same thing. All these mean the same thing. And what about the range? What about the range of this function? Actually, to get the range of this function, to get the set of all possible outputs, we plug in the domain. We are saying that x should be greater than or equals to 1. So what if I plug in 1 here? You realize this will give me a 0. The square root of 0 is 0. So this means that the range should be such that this is greater than or equals to 0, because the minimum value of x we can use is 1. So I can say the range of the function f is actually the set of f of x such that x minus 1 square root is greater than or equals to 0, is greater than or equals to 0. And how are we getting this? By plugging in the minimum value of the domain of this particular function. So basically, very important to take note about the radical function. We are looking at the square root. If we are getting a negative number, it means that the function is not defined. It means that the function. So let's have another example here. Example 4, an example of a polynomial function. X is equals to 2x minus 1. H of x is equals to 2x minus 1. What is the domain of this function? You realize for this particular function, when we plug in any value of x, will actually give us an output, be it positive or negative. So this means that the domain of this function is actually the set of all real numbers. In simple terms, x ranges from negative infinity to positive infinity. So I can simply say the domain of h is actually the set of x values such that x is a member of the real numbers and that x ranges between negative infinity to positive infinity. That is the domain of this function. What about the range? The range also, you realize, if I plug in a value here of any natural number, I'm getting an output. So this means that the range will also be actually the set of h of x, the set of h of x, such that this is also in real numbers, because when you plug in a real number, you are getting a real number, and such that this is h of x, it ranges between negative infinity to positive infinity. So is less than or equals to x minus 1 less than to infinity. The h of x ranges between positive infinity to negative infinity. Now, that is simple. Let's have another example of a trigonometric function. G of x is equals to tan x. What is the domain of this function? Now you realize we all know that tan x is equals to actually sine x over cos x. So we have now transformed this trigonometric function to another trigonometric function, which is basically a kind of a rational function. And we know for rational function, if we want to determine the domain, then we consider the denominator. If the denominator is giving us a 0, that means we cannot divide the numerator by a 0, and therefore the function is not defined at that point. So what we do, we exclude that value which will give us a 0 on the denominator from the domain. So this implies that in order for this function tan x, which is the same as sine x over cos x, to be defined, then cos x should not be equals to 0. It should not be equals to 0. If it is negative, it is okay. But if it is 0, it will give us a problem. So what is the value of x that will give us 0 when we substitute it to the cos function? That is, what is cos x that is giving us a 0? You realize it is pi over 2. That is 90 degrees. So this means that x should not be equals to pi over 2. But you realize it is not pi over 2 alone that is giving us a 0. It is not cos pi over 2 alone that is giving us a 0. There are many. There are others like 3 over 2 pi and some others, depending on the unit circle. As you move along, you'll get those values. So we need to come with a proper way of including all those values, and you realize it is basically all these values can be defined by pi over 2 plus n pi, where n is an integer, or rather n is an integer. So therefore it means that my x should not be equals to this set of all angles that will give me 0 on the denominator. So the domain of this function g is the set of x values such that x is not equals to pi over 2 plus n pi, where n is a member of the positive integers, like that. So this is how we get the domain of such a function. That is basically how we get the domain of the trigonometric function. Transform it to this sine over cos, consider the denominator, and exclude the points which are giving you a 0. Let's have another example and call this example 6, which this example now is a bit amazing in a way, because we are having a radical function anyway, and I'm having f of x is equals to x squared minus 5x plus 6 square root, which is as good as writing this and say power a half. That is why I'm saying it's a radical function. So you realize for this function to be defined, you know, when we talk about domain, we want to exclude that point. When we want to define the domain of a function, especially the natural domain of a function, where all inputs are actually giving us an output, when we want to define that particular domain, we exclude those inputs which will not give us an output. That is the most important thing. So we are saying, we know that this function will be defined for every point of x except for the point whereby we will be having a negative number, because once we substitute a value of x and it's giving us a negative number, we won't be able to find the square root when it comes to real number system. So this means that my x squared minus 5x squared plus 6 must always be greater than or equals to 0. So x squared minus 5x plus 6 must be greater than or equals to 0 for this function f of x to be defined. Now, let's solve for x here and see what are the values. We need to have two numbers such that when we multiply the two numbers, we are getting 6x squared, and when we add the two numbers, we are getting negative 5x when we add the two numbers, and these numbers are actually 2 and negative 2 and negative 3. So this is as good as saying x minus 2 or minus 3 into x minus 2 is greater than or equals to 0. Now, you realize we can go ahead and say x minus 3 is greater than or equals to 0 and x minus 2 is greater than or equals to 0 because the two are connected by multiplication, which is as good as saying x is greater than or equals to 3 and x is greater than or equals to 2. When you look at those two values and we want to define the domain of this function, you realize the domain here will not be explicitly defined. The domain will not be explicitly defined. And how is that? The first case is telling us that x should be greater than 3. The other case is telling us that x should be greater than 2. Does this mean that 2 is included in the domain or not? Because if we consider this case, we are actually excluding this. We are including this. But when we consider this case, we are actually excluding this case. So what is the explicitly defined domain for this function? In order to get the explicitly defined for this function, we do what we call sign test analysis. We do a sign analysis test to see what is actually the implicitly defined domain of this particular function. And how is that? I can first set x to be equals to 3 and x to be equals to 2 and do the test analysis and see the values below or above 3, to the right of 3, and the values to the left of 2, that is below 2, and the values in between 3 and 2 to see which values actually belong to the domain of this function and which values do not belong to the domain of this particular function. So with this, we can do the sign analysis test. Maybe we do it on a fresh page. Maybe we do it on a new page here such that you guys get to understand it even better. So I'm having my x is equals to 2 and my x is equals to 3. Remember, it was x is greater than or equals to 2 and x greater than or equals to 3. But we only write this because we want to do the sign analysis test. The sign analysis test. And the sign analysis test is done to determine where the function is actually defined by testing the points between 3 intervals, by testing the points between 3 intervals. And what are those 3 points? The 3 points are actually these here. We are having 2 and 3. So this is the first, second, and third. So we will test for the values to the left, that is below 2, the values between 2 and 3, and the values that are greater than 3 to see where exactly the function is defined. So you realize our function or our condition was x squared minus 6x, x squared minus 5x plus 6 is greater than or equals to 0. That was our function. That was our condition based on the function because it was a radical function. So let's test for the point to the left of 2. So testing for point to the left of 2 and say we need to pick a point here. We need to pick a point here which is less than 2. We can say 1. So say x is equals to 1. Let's do the sign analysis test for the point below 2 and realize we'll be having from the function x squared or the condition minus 5x plus 6 greater than or equals to 0. We substitute in the value 1 which is to the left of 2 and we'll be having 1 squared minus 5 into 1 plus 6 being greater than or equals to 0. That is the condition. And you realize here I'm having 1 minus 5, 1 minus 5 that is minus 4, then plus 2, plus 6 that is 2. So I'll be having 2 being greater than or equals to 0, which is true and it is positive. It is positive. The value here is positive. Our main interest is the value being positive or negative. That is why we initially said the whole expression here should be greater than or equals to 0, meaning it's positive. So at the point to the left of 2, it is positive for our function. Remember, maybe I should write the function somewhere. Our function was f of x is equals to x squared minus 5x plus 6 square root. This function is only defined when the value is positive. That is why we are doing the sign analysis test. So the value between, let's test for the interval between 2 and 3. So testing for the point between 2 and 3. Testing for the point between 2 and 3. Let's say we need to pick a point between 2 and 3. X is equals to 2.5. It is somewhere here, so it's in between. So from the condition, x squared minus 5x plus 6 is greater than or equals to 0. It means that 2.5 squared minus 5 into 2.5 plus 6 will be greater than or equals to 0. You realize when you work out here, you are actually getting negative 0.25. So negative 0.25 is greater than or equals to 0. And you realize it is not greater than or equals to 0. Actually, it is less than. So it is not equals or greater than or equals to 0. So it is positive. It is positive. And I'll come at the top of my line here and say it is negative here. Then testing for the point to the right of 3. Say x is equals to 4. Now we are testing for points which are greater than 3. Let's say 4. So from the condition x squared minus 5x plus 6 is greater than or equals to 0. When I substitute 4, I have 4 squared minus 5 into 4 plus 6 greater than or equals to 0. And here when I substitute, because this is 16 minus 20, 16 minus 20, that is 4 plus 6, that is 2. So I'm having 2 greater than or equals to 0. Again, it is positive. It is positive. So I come here and say this part is positive. And now I know which part should be excluded from the domain. The only points that we are not testing is actually at 2 and 3. Because we know when we test for these points, for sure, they'll give us a 0. If you substitute 2 here, it will give you a 0. That is why we are not testing for this point. So these points should be included because they're giving us a 2. So we substitute here 2, we'll be having 4 minus 20, that is minus 6 plus 6, that is 0. If I take 3, substitute here, I'll be having 9 minus 15, that is minus 6, plus 6, that is 0. So I'm not testing for 2 and 3 because already they are included based on the fact that we were having initially here, we were having x minus 2 is greater than or equals to 0 and x minus 3 is greater than or equals to 0. So these values are actually giving me a 0. So these two values are to be included. But now I have a positive, meaning all values below 1 should be, all values below 2, to the left of 2, should also be included, and 2 must also be included. Then we exclude these values, all values from 3, which 3 is included, forward, they are also to be included. So you realize my domain is actually divided into 2. This part here, this part here. So you need to unite them. That is why we are using the union. So I can come here and say, thus, the domain of the function f is actually the set of values from negative infinity, that is below 2, but this is not included to 2, and this 2 is to be included because it is giving me a 0. That is why I have a square bracket. Whenever we have a square bracket, it means the value is actually included. And when we have a curly bracket, it means it is not included. Then union from 3, which is also included, to positive infinity, which is not included. So there are some values here between 2 and 3 which are excluded because they are actually giving us a negative. And how is that? Based on the sign analysis test. It is based on the sign analysis test. So very important to take note about that. At times we need to do the sign analysis test to get a better understanding of the domain of a given particular function. Don't forget, this was our original function. This was the original function, and this is the domain, and this is the domain. So let's have another example and call it example 6. I have a function f of x. This function f of x is defined by x squared minus 4 all over x minus 2. And the question is, what is the domain of the function? Very simple. I know we are now good with the rational function because we know for rational function, the function will always be defined except where the denominator is equals to 0. So in order for our function to be defined, the denominator must not be equal to 0. So this means that my x minus 2 should actually not equals to 0. So this means that my x will not be equal to 2. Now, the domain of this function f is actually given by the set of all real numbers, x such that is in real numbers, except when x is equals to 2. So x must not be equal to 2. We are excluding that part, except when x is not equals to 2. Now you realize this function, however, can be simplified. That function can be simplified. The function f of x is equals to x squared minus 4 all over x minus 2. This function can be simplified such that f of x is perfect squares here. We'll be having x plus 2, x minus 2, because when we expand these two, we are actually getting the numerator all over x minus 2, such that I'm getting my f of x to be, we cancel this and that, and we're having x plus 2. The question is, this new function, which is obtained by simplifying the original function here. This new function that is obtained from simplifying the original function, does this means that this has its own domain? Because actually, when you observe at this function, when we take any value of x, it will give us an output. It will give us an output. So the question is this function, its domain be the set of all real numbers? Does this mean that the domain of this function to be the set of all real numbers? The answer is no. The answer here is no. Why is that? Because with simplification of a function, we have to keep the original domain. So since this function is obtained from the original function here, then this means that the domain of this function is actually the set of all real numbers, except when x is not equals to 2. So this is also the domain for this function. Despite that, when you try to plug in any value, it will give you an output, but we always have to retain the original domain. So very important to take note about that. So we can even have an NB and say, with simplification, keep the original domain. Very important to take note about that. Keep the original domain. And now you realize, if we try to sketch this function, we try to sketch the original function. F of x is equals to x squared minus 4 over x minus 2, which is the same as the simplified function f of x plus 2. If we sketch this function, actually the graph of this function is just the same as this function here. So let's sketch the function. Let's sketch the function f of x is equals to x squared minus 4 over x minus 2, which is the same as f of x is equals to x minus 2, x minus 2. So these two functions are actually the same. So we need to come up with a sketch of that particular function, and this can represent the sketch of that particular function. It is easier to work out with the simplified when it comes to sketching. Now you realize, suppose this is 1, 1, 1, 1 like that. Then 2, 3, 2, 3, 2 like that. So f of x, this is my f of x, this is my x, the function is x minus 2. So when x is 0 here, when x is 0 here, actually the simplification is positive. So this is plus 2. So when x is 0 here, my f of x is 2. And when my f of x is 0, my x is negative 2, somewhere here. And you realize there's that point which we know the function is not defined. That is when x is not equals to 2. So that point, when x, assuming x is equals to 2, my f of x will be equal to 4. Let's say it is some point here. So that is now my graph. That is now my graph, a straight line like that. Sorry for the space, but I hope you guys can see it. Now, you realize, since the function is not defined at x is equals to 2 here, this is x is equals to 2, we have a removable discontinuity at this point. That is why actually I have a hole on that graph, and that is called a removable discontinuity. And why is it called a removable discontinuity? It is removable because we can use a single point to fill this hole. And that point that can fill this hole is 2, 4. We can use a single point to fill this hole. So whenever we have a function that we can only use one single point to fill that function, to fill that hole, is actually called, that discontinuity is actually called a removable discontinuity. Later on, just after this tutorial, we will be discussing about continuity and discontinuity of a function. You'll get to understand that even better. So Basically, the removable discontinuity is when we have a whole, and we have a whole if we can cancel out, and that cancel out is in bracket, is in quotation, because it is not the proper word, but allow me to use it. If we can cancel out the domain problem, then it's a whole. But if we cannot cancel out the domain problem, then it's an asymptote. We will also discuss about asymptote and get to see it even better. So most important, when we simplify a function, we will always keep the original domain. And when we can simplify a function, it means that we can cancel out the domain problem, and therefore that particular function has a whole. That particular function has a whole. That is a removable discontinuity. But if we are actually having a function, and that function we cannot actually simplify or cancel out the domain problem, then that particular function is said to have an asymptote. Now let's have another example here, trying to tell when we are having a removable discontinuity, or rather a whole, and when we are having a vertical asymptote, meaning we cannot remove the domain problem. Suppose I have a function, say the same function, x squared minus 4 over x minus 2. We just say that this function is not defined at x is not equals to 2. The function is not defined at the point x is 2. That is why in the domain we are saying x is not equals to 2. So now you realize if we substitute 2 to this function, we will actually have 0 on the numerator and 0 on the denominator. That is, because this is giving me 4 minus 4 is 0, 2 minus 2 0. So this function is giving me a 0 over 0. That is, if we plug in 2, we actually get 0 over 0. Now, because we are having 0 over 0, it means that we can cancel out the domain problem. So because of this, we can cancel out the domain problem. And allow me to quote that out, the domain problem. We can cancel out the domain problem. And because we can cancel out the domain problem, it therefore means that this function at the point x is equals to 2, it is having a whole. It has a whole. When do we say we are having a whole? We are saying we have a whole if we can remove that particular discontinuity. That is what is called the removable discontinuity. So thus we can say, thus it's a whole, the function has a whole, it's a whole, and allow me to quote that, when is it said to be a whole? When we can remove the discontinuity. I will just write in short form, the discontinuity, when we can remove the discontinuity. So whenever we plug in the value where the function is not defined and we are getting 0 over 0, it means that the function has a whole and that we can cancel out the domain problem such that the function becomes continuous, such that the point is called, the function is said to have a removable discontinuity. Now, suppose I have another function, g of x, and this g of x is x over 3x over x minus 4. You realize this function will be defined except for the point where x is 4. So in the domain, actually, x is not equals to 4. Now, you realize when we plug in the value of x at the point 4, on the numerator, we are having 12 over 0. So we are having a number over 0. If we have a number over 0, we say that that point is actually a vertical asymptote. Unlike this case where we are saying this point is actually a hole, here we say that point is actually a vertical asymptote. And it happens typically when we have a number over 0. This happens typically when we have a number over 0 and we cannot remove the domain problem. So we can say if we plug in if plug in 4, okay, we get 12 over 0. So this means that it's a vertical asymptote. Okay, we will discuss about a vertical asymptote and horizontal asymptote, and it happens typically when we have a number over 0, a number divided by 0. So in simple terms, we cannot remove the domain problem. We cannot remove the domain problem. So that is how we can distinguish, how we can remove the domain problem and where we cannot remove the domain problem. We can only remove the domain problem when we have a hole. And how do we identify a hole? When at that point the function is not defined, we are having a 0 over 0, then that point is a hole, and we can cancel out the hole by using only a single point, and therefore we say the function to have a removable discontinuity. But at this point, when we are having a number over 0, it means that we are having a vertical asymptote, and because of that, we cannot cancel out the domain problem. Thus, the function is said to be discontinuous. We cannot remove the discontinuity of such particular function. Now, we can finish this by saying, suppose we have another example. Let's call this example 8 and say f of x is equals to 2 plus x minus 1. Maybe we can use this to determine range, actually, because we have actually been talking about the domain all along. But the domain is most challenging compared to the range, because once you identify the domain, it is very simple to get the range. So what is the domain of this particular function? We all know that for this radical function, the function will be defined except when we are having a negative here. So this means that my x minus 1 should not be equals to 1, implying that x should not be equals, should actually be greater than or equals to 0. Here, we only have positive. So let's have another example and call this example 8. Suppose I have a function f of x is equals to 2 plus x minus 1 square root. I need to get the domain and range of this function. Actually, we will talk about domain, the range also, because we have been all along talking about the domain. But actually, the domain of a function is the most important aspect to determine, because once you get the domain, it is easy to identify the range. So we realize, we all now know that this function is defined except when we are having a negative here, because we said for real numbers we cannot compute the square root of a negative number. So this means that this value here should be actually greater than or equals to 0. So x minus 1 should be greater than or equals to 0, implying that my x should be greater than or equals to 1. So the domain of this function is such that x is greater than or equals to 1, which you can also write as 1, because 1 is included, all the way to positive infinity, which is itself is excluded. Now, what about the range? What about the range of the function? Now, for the range of the function, to get the range of the function, we plug in the value of the domain. And you realize when I plug in 2 here, we will be having 0. So f of x is 2. So the range is such that my f of x is greater than or equals to 2. Because I'm not having any value less than 1 that I'll plug in, but it is actually from a 1. So it is, my f of x will be from 2 and above, which is obtained by simply plugging in the domain, that is 1. This can also be written as 2 to infinity, which infinity itself is not included. That was simple. Maybe we have another example. My y is equals to x plus 1 over x minus 1. Now, it's a rational function. Do we know that for rational function, the function is defined except when the denominator is equals to 0. So for this function to be defined, x minus 1 must not equal to be 0. So this implies that x should not be equals to 1. And therefore, the domain of this function is actually the set of real numbers, such that my x is not equals to 1. My x is not equals to 1. That is the domain of the function. What about the range? Now, for the range, we can also plug in the value of the domain. And when I plug in the value of the domain, you realize here I'm getting a 0. So it means that the range cannot be 1. The range cannot be 1. We can have any other values but not 1. So we can say the range of the function y is the set of values of y, and this is in real numbers, such that my y is not equals to 1. My y is not equals to 1. Simple. But we realize there is another way we can determine the range of this function, because we are actually, in simple terms, it is like we are saying what is the domain of y in this function. The domain of y in this function is actually the range of that particular function. So how can we determine the domain of y in this function such that we get the range of the function x? It is very simple. To find the range, we can find the domain for y, which will be the range for x. So from y is equals to x plus 1 over x minus 1. Let's make y the subject. We'll be having y into x minus 1 is equals to x plus 1. And this will give us xy minus y is equals to x plus 1. We are making x the subject, sorry. And this is as good as saying xy minus x is equals to 1 plus y. And we factor out x, I'll be having x y minus 1 is equals to 1 plus y. And I'll be having my x equal to y plus 1 over y minus 1. And you realize this function is literally somehow the same as that function there. It is basically the same, just like that function there. So what is the range of this function? The range for this function, we all know that this function will be defined, and in order for this function to be defined, y minus 1 must not be equals to 0. So this means that my y should not be equals to 1. So this is the domain of this function, which is the range of this particular function here. The domain of this function is the range of the original function. Actually, this is the original function here. So that is how we can get the original function. And we realize at the point x is 1 for the original function, we are saying the function is not defined. And when I take I substitute x here, it is giving me a 0. But and here I'll be having 2. When I substitute x, I'm getting 2 over 0. So this means that because I'm getting 2 over 0, it is not a whole, but it is a vertical vertical asymptote. It is a vertical asymptote, meaning it is cutting the x-axis at some point. It is a vertical asymptote. But we realize for this point here now, y is 1. When I substitute y is 1, when I substitute y is 1 here, you realize this function is giving me a 0 and 2, so I'll be having 2 over 0. But now it is a function for y, so this is a horizontal asymptote. This is a horizontal asymptote. That is basically is not important for this tutorial, but that is how we can also determine the range and the domain of a function. Now, domain and range of a function is applicable to real life situation. And how is that? Maybe we can have one single example as we mark end of this tutorial. So world problem that involves domain. World problem on domain and range. Now, suppose I have a box, let's say not a box actually, but I have a piece of material and I'm to generate a box from that piece of material. This is the material I have, and this material measures 16 centimeter by 30 centimeter, like that. Now, I need to generate, generate a box from this piece of material. So, and this piece of, a box is to be generated by folding this box in the measurement x by x, by folding this box in square x by x. Maybe my drawing is not cool, but you guys will understand this, x by x. So when I fold this piece, and this piece, and the other piece, I'll be having a kind of a box. Now you realize at the end of the day, I'll end up with a box like this. Now here is the problem, because I didn't attend a 3D drawing class, but I'll try my best. This is all I can try anyway. So I'm having my box like that, such that you realize the dimension here is actually 16 minus x minus x. So the dimension here is 16 minus 2x. The dimension here is 30 minus x, which is 30 minus 2x. And the dimension here is actually x. The question is, what is the maximum measurement that you can fold this material in order to get a box? And that is the domain, because there's that point you can fold the box, you can fold or you can cut, and you're not getting a box. It is not giving us the desired output. So suppose I cut this piece to the far end. You realize I won't be able to cut another piece here to fold on this side. I will only have cut this side to fold that way, but it won't be able to cut again to have that side. So if I find the volume of this function, I express the volume as a function of the dimension, I'll be having the volume as a function of x to be 16 minus 2x multiplied by 30 minus 2x multiplied by x. This is the volume as a function of x. The question is, what is the domain of x? The domain of x. What is the domain of x? When I say what is the domain of x of this function, I simply say, ask, what is the value of x here that we can cut to obtain a box? What is the range? Now realize, like I was saying, if I cut from the far end to this far end, I won't be able to cut on this side, and thus I won't achieve a box. But realize I can cut here to halfway, that is 8, and I can cut here to another halfway, that is 8. So it means that the maximum also here, I can cut here to halfway, that is 30, and I can cut here to 30. But I mean 15, 15. But now this is 8, 8. So we consider the least maximum, which is actually 8 and 8. So it means that the maximum that I can cut is 8 on either side. Now, what is the minimum? We know that in order to generate a box, at least I should cut here and fold. Otherwise, I won't be able to generate a box. So therefore, it means that my dimension should be greater than 0, meaning I need to cut to have that. So the domain will be such that 0 is less than or equal to x, less than or equals to 8. And this is the domain of the volume as a function of x. That is the domain of the volume as a function of x. So domain problems can also be applied to real world situation. Now, that marks the end of the domain and range on this tutorial. What we are going to discuss on the next tutorial is on even and odd functions. Even and odd functions. When is a function said to be odd and when is a function said to be even? Suppose we are given a certain function. How do we determine that particular function is odd or even? To know that, subscribe, click the notification bell, and wait for the best tutorials on even and odd functions. Thank you.